So 1, 2, 3. Here we go. So lesson 2, tangents, derivatives, and normals. You might have heard a little bit about tangents in GCSEs. You might not have heard of normals, but do you remember things like perpendicular, bisectors?
Yeah.
Yeah. Well, what's the relationship between a line and its perpendicular?
And it's what? They have 90 degrees at the...
Yep, 90-degree angle. And what's the relationship between their gradients?
The same.
Oh, they're inverse.
The squares. They're inverse. They're the opposite.
Yeah, opposite. You flip it. So if this gradient was 2, what would be the gradient of it?
-2.
Close?
Half.
Negative a half, yeah. So like the negative reciprocal. So you change the sign, and you change the and you make the inverse. So if a line had a gradient of negative 2/3, what would be the gradient of its perpendicular?
3/2.
3/2, yeah, good. So you change the sign and flip it. That's right, so that might be helpful to be aware of today. Normals are perpendicular to a tangent. And derivatives are just practicing derivatives. You're pretty good at just in general finding dy dx. So I've popped in a few slightly more challenging ones where there's fractions involved. So tangents. So you usually find an average rate of change between 2 points by drawing a secant. Have you heard of that word before?
Yeah, that's my life.
It's the lesson. A secant. A secant, kind of like a chord. Remember, like a chord? Chord just connects 2 points on a curve. So a secant. Some people say the word chord. A secant. So usually we find the gradient by connecting 2 points on a graph and using the formula rise over run. Yeah. So showing you kind of an example of that, like a secant connects 2 points. But that's meant to be a straight line, by the way. Straight line connecting 2 points. And we would find the rise and divide it by the run. So that's our secant. That's the way we've normally done it in coordinate geometry. So get 2 points and find the rise over run, or use the gradient formula instead. My2 minus y1 over x2 minus x1. Before the days of calculus, the only way they could find, so that's the average rate of change between 2 points. Before calculus, the only way they could find the rate of change at 1 point only, as opposed to between 2 points, was to draw a tangent. Have you heard of tangents before, where kind of makes it, in theory, just touch at 1 point? And that's meant to be a straight line that represents the gradient at that point. So everyone will draw a tangent slightly differently. Like, why do you think this is not quite right? Yeah, good. It shouldn't so much crossover. And does the gradient at that point really look like it's as flat as that? I think it's probably a bit steeper. So you're using your eyes a lot. Why do you think realistically this one's not good?
They're touching it in too many points.
Yeah, too many points, exactly. It's meant to, in theory, just touch at 1 point only, and it's maybe a bit too steep. Would you say just a bit less steep for that one? So it's pretty hard to do, as you can see. Like, everyone's going to completely differently draw a tangent. So in the old days before calculus, the only way you could find a gradient at 1 point only was to draw this tangent and find the rise over run of that tangent. So yeah, basically draw the tangent, pick 2 points on the tangent, and do rise over run. Was the only way that you could find it at a particular point, like point P. So I'm just drawing the point P. Whereas here I found the average gradient between P and Q, which is a different answer to that. So I've got to fill in the stuff up here, just stuff to fill in. For your calculus, the only way you could find what we call the instantaneous rate of change, meaning the gradient of the curve at 1 point only, was to draw a tangent at that point as accurately as you could, and find the gradient of that tangent using rise over run. This was before calculus was invented. So for the sake of paying respects to these old school methods, let's try to find the gradient of the curves below by drawing a secant. So we're going to do rise over run of this one, and using a tangent that I'll explain to you how we're going to use tangents a bit more. Okay, so rise over 1. You can also do, like, remember another formula for the gradient is m equals y2 minus y1 over x2 minus x1. Remember that formula from coordinate geometry? And all we're doing, we're not finding the equation of the line, we're just finding the gradient. So for point P and point Q, we could write out their coordinates, that might help. What's the x coordinate of P? X, yep. What's the y coordinate of P? F of x, yeah. Upper coordinate would be this one here. What's the x coordinate of Q? Yep, x plus h. And the y coordinate of Q is f of x plus h. H is just the, like, you know, the horizontal distance between these 2 points. So we can call the first one x1, y1 to use in the formula. The next one could be x2, y2. If that works. And we're actually going to derive the formula for finding for using calculus. So gradient, we're using y2 minus y1. So y2 is f of x plus h. y2 minus y1 and minus f of x. So this on y2 minus y1 over x2 minus x1. So x plus h.
Might have the h in mind.
Minus x. Does anything cancel out here? Yep, down here, yep. These two will cancel, yep. Yeah, well that bit, yeah. X plus h, these, the x minus x will cancel. So f of x plus h minus f of x is still the same as before. But what's the new denominator? H. H, yeah. So that's kind of like a formula for the gradient. And a little clue is that's the theory of calculus.
What?
So, because calculus is kind of still using the gradient formula, like y2 minus y1 over x2 minus x1. And they use this idea that there's point x and f of x. The other point is h. Like there's a distance of h between them horizontally, like horizontal distance, h for horizontal distance. So this one must be x plus h, and that must be f of x plus h. So we've just come up with a formula for the gradient between 2 points. Very similar formula for the gradient here, but the theory behind calculus is that instead of q being some distance away, q is getting infinite. This point q is shifting infinitely closer to p. So q, how on earth can we depict this? So this point q.
QQ.
Let's do it in
Yeah, Brian will explain that then.
that point. It's moving. If you can show it anyway, it's moving infinitely close to q.
What
Q is moving. So q is moving. Point q is moving infinitely close to p.
Why can't you say P is moving infinitely close to Q?
You could, but the way they set it up to begin with was they q's moving closer to p. But yeah, you could have done it the other way. And it's because I've decided to make the tangent. That's a very good point. I decided to make my tangent at point P. I probably should have stated that in the question, because I decided to draw my tangent at point P. So instead, the theory is Q is getting infinitely closer to that point, because that's where I drew my tangent.
Infinitely closer to P.
Yeah, so point
P.
Q is getting infinitely closer to point P, so that the distance between them, the distance between the 2 points, is approaching 0. Is approaching 0, like the horizontal distance between them specifically. These approaches.
So that's the distance.
Yeah, it might seem so obvious, if Q is getting infinitely closer to P, the horizontal distance between them is getting closer and closer to 0. So if this thing keeps moving infinitely closer to P, then that little distance there is approaching 0. So by that I mean like H is approaching 0. So that in symbols, that's what I've said in purple. So as point Q is getting infinitely closer to point P, the horizontal distance between them, H, is approaching 0. And this is an important thing because we use that in the notation. So we could then say, using the whole limit idea, we can still use this general formula. So it's still this general formula here, because we've got f of x and x plus h, and x plus h, f of x plus h. We've still got the same two coordinates. But what we just do is, in front of them, we just pop this. The limit as h, the horizontal distance between the points, gets closer and closer to 0. It never hits 0, just gets infinitely closer to it. Of this thing is this thing. Of f of x plus h minus f of x over h. I'll just write it lower, sorry. I need a little space. So again, that was the limit as h approaches 0. Just writing this thing here. Maybe I'll write it in red so you can see where it comes from. F of x plus h minus f of x over h. That thing is the derivative. That's dy dx. So this is the formula that underpins dy dx.
dy dx?
Yeah, oh, you don't know what dy dx is, the derivative. So I'll say, let's use Newton's notation of f dash x, because that's what we're sort of using here. We've got f of x and that kind of thing. dy dx we tend to use when we're dealing with the letter y, but if they call the function f of x, we use this thing. So f of x is the derivative. So this thing is, for those from GCSE who remember it like dy dx, something like that. It's like dy dx. But if we're using the notation f of x instead of y, then we say f dash x. It's a bit easier to write too.
Wait, what did you say f dash x?
F dash x means the derivative. The derivative. Like the derivative is a function that represents the gradient. Yeah. So the function that represents the gradient is this thing. This is the theory. They call it first principles, meaning like the theory behind calculus. So there's a special name for this thing. They call it, I'll just write it, first principles. A bit of a drag. If you did HL, and I think Mr. Akima with his HL group are doing the calculus option, they have to do calculus in the calculus option a lot using this formula, but we just kind of pay a bit of lip service to it, and then we move on to just more practical calculus. Pretty advanced practical calculus, but we don't spend as much on the theory behind calculus and first principles. In higher level they do, but I just sort of have to kind of show it to you, and then we kind of move on. More so do you understand what this means? The limit as h approaches 0, meaning that q is getting infinitely closer to p. So the horizontal distance between them approaches 0. So that's why it's formally, it's not the average gradient between 2 points, it's meant to be the gradient at that point only. Is meant to be the gradient at that point only. So that's a tangent. So that's what calculus was all about, finding the gradient at one point only. So we kind of use these principles to do that. And then, again, it's going to be very rare that you'll be asked in an exam to use first principles in SL to find the derivative. But just in case you do, we'll do a few problems on it. Most questions are using the short method. Like, where you take the exponent, multiply it by the coefficient, and subtract 1 from the exponent. That's the short method. So we're just doing the long, old-fashioned method to start with. So use this first principles method. You don't have much space to do it, so we'll just do it quickly. To find the derivative of x squared at x equals minus 2. Oh gosh. So we've got to use, where have I got that? Okay, yeah. So it's as if we've got a tangent at x equals minus 2. So we've got to use this thing here. So the one on the right is what we're using. So we might want to write that out. So you might want to say, remember, for a tangent, h approaches 0. So for a tangent, if it was like this one on the right, the horizontal distance between the 2 points is approaching 0. They're getting infinitely closer and closer together. So we can use this formula here, which we'll write out. The limit. If you don't want to write the formula again, that's okay, because you don't have much space. As h approaches 0. Do you want to write the formula again, or do you want to just go straight into something?
Yeah,
again?
right again.
Yeah, okay. Because it's pretty weird. So you might want to look back and see how did I start to sub stuff in. So it's helpful if you've got the formula written. Okay, h. Just that bit is what we need to write. We don't need to write f dash x. At this point, they assume you know it means a derivative. And they're asking for the derivative. So that's why we're using this. Now what we've got to do is we've got to use x squared. So whenever you see x here, we've got to replace it with x plus h for that bit. And this is just the function. So I'll rewrite the whole thing with the function subbed in. So f of x plus h, in this case, will be, instead of x squared, it's going to be x plus h squared. Might seem a bit weird. F of x plus h, it's as if we're just replacing the x with x plus h.
Pardon?
Oh, because our function this time is x squared. So now we're going to, instead, that's a general formula, now we're going to apply that formula to this thing. And then we expand and
Oh,
simplify.
apply the formula to that. I thought you were applying that.
Yeah.
So why are you squaring that if that's
No, you
yeah.
put in x squared, I forgot to do.
That, yeah. So all I'm doing is, instead of wherever I'm using this, writing this thing, but because it's function of x plus h instead, I replace the x with x plus h. What do they call that again? Like composite functions. Remember composite functions? It's like I'm subbing x plus h into that thing.
But why would you do that if that's f of x that it doesn't
Yeah.
say f of x plus h?
Yeah. So because these two are meant to be related to the same function. That's a good point. Yeah. These two are meant to be related to the same function. So that is the function, and this one is the same function has to be related to the same function, but instead of x, they have x plus h, which seems a bit weird. So then what would I write here? Minus x squared, yeah, just what the function is, over, and h is just the horizontal distance. And then what we've got to do is now expand and collect like terms and cancel down if we can. Here.
Do I say the window and everything?
Yeah, it's not a capital space though. So, and it's a bit frustrating, but you've kind of got to bring this limit as h approaches 0 stuff down with you. Don't skip it out, you've got to kind of bring it down with you on every step. If you're being asked to solve something to find a gradient or derivative, using first principles. So to save a little bit of space, x plus h squared would be like x plus h plus x plus h. What would that be? Yeah. So if you don't have to write it out, you can write it out if you've got the space of h. But if you don't have the space, then we can probably think what would it be when this part's expanded? X squared. Yeah.
That's alright. Are you recording?
Yeah.
That's x.
Yep.
That's x.
Yep. Good. Yeah. So the h plus xh. 2xh. Yeah. Plus h squared. That's what that thing is. Maybe I'll do this one in a different colour just so you can sort of see where this one's coming from. Minus x squared. Or h. So that's what we just did. There wasn't. I should have given you more space. Sorry. I kind of after I printed it, I realised there's not enough space. And then I'll move over to this side. And then does anything cancel out there at all in the top? Yeah, sweet. You'll start to notice lots of stuff will cancel out and you'll just end up with something really simple in the end. Because by the way, if you were to use the short method, what's the derivative of x squared? Something really basic. 2x, yep. So strangely enough, the purple part here is all going to simplify down to be 2x in the end. Because at some point, it's only at the end, towards the end, that you kind of acknowledge this part, h approaches 0, and then you kind of sub in h as 0. But at the moment we can't do that, so we can't sub in h as 0 yet, or else we'd be dividing by 0. So we've got to cancel down first. Stuff here. So I've still got to bring this thing down, lim, as h approaches 0 again. It can feel very tempting not to write that, but we have to for using first principles. So, do you want to take out a common factor, or can you just see that h is cancelled down?
Yeah.
Yeah. So once I've cancelled down the h's, what would be left on the top?
2x plus h. Or you can do 2x plus h squared.
2h.
It's 2x plus h squared or 2h squared plus h. I mean
Yeah.
2x
And that is
plus h.
And that is a tricky one, so it might be worth just factorising the top first. Let's factorise the top first, because it is hard to do all that in your head at once. So when you just take out h as a common factor here, you've got 2x plus h, so that might be a lot safer.
Plus your h's can cancel out.
Yeah, those ones cancel out. So doing that little step there is probably a good move, because trying to cancel it all down in your head there can get a bit messed up. So taking that as a common factor and then cancelling down is a lot safer. So then we've got this limit as h approaches 0 of 2x plus h. So now there's no h in the denominator. It's pretty safe that we just now sub in h is 0.
No way.
Wait, why is h 0?
As h.
Oh.
I know, yeah. It's infinitely approaching 0. So the fact that's a good point. It doesn't actually equal 0. You've got a good point. It's infinitely approaching 0 to the point where the plus h is irrelevant.
Oh, okay. So it's just 2x.
Yeah. So, yeah.
But then would you plug in the negative 2?
And then at this point I might just say, nah, we just go like that, 2x. So at that point you might just say the derivative, because this thing equals a derivative, I just didn't have to write down equals
So
x
if
x.
h was approaching 2, what would you do?
Yeah, good point. Then it wouldn't cancel down to that, basically.
It'll be 2x plus
Why do
2.
we just
That's
take
it.
it? Why do we keep moving h? Like, why?
Yeah, that's a very good point. As h is infinitely approaching 0, it's becoming so small that it's irrelevant to the overall gradient
But
value.
if it was 2, it would be 2x plus 2 then.
Yeah, but if
So we're
we
going
wouldn't,
plus x plus 0?
if it was for finding the gradient of a tangent though, we wouldn't say 2, because instead the theory behind calculus is that it's getting infinitely closer, so that h is not approaching 2, it's approaching 0. So 2 point is this point. Yeah, so that's just because the theory of calculus says that it's approaching 0.
Alright.
I think. Because we're trying to get a gradient that would be as accurate as possible for this tangent. So in theory, it's approaching 0. So yeah, let's write that point that you guys were asking about, which is why do we just say h is 0 now? As h is approaching 0, you can just write that, h approaching 0. Its value is so small that it's almost, would you say irrelevant?
But if it's always... How is it approaching 0? This, like, because it's a horizontal space between the 2 points. Oh, I get you. It's like
Yeah.
a distance and then...
Yeah, that's right. As that's approaching, the horizontal space between this little thing here is shifting over and over, infinitely closer. So infinitely closer, because that's just the theory of calculus, is that they're shifting infinitely closer to the point where the tangent is. So that's why, and it's only at this point, once we've it's not really until you've cancelled off the h. You'll find if you do first principles differentiating all the time, you always end up cancelling off the h. And it's not until you cancel off the h that you're allowed to sort of acknowledge that h is almost at 0, because otherwise it's like you're dividing by 0, and then it wouldn't work. So that's a lot of work to do what you know to do already. Like the gradient of this is just 2x. Let's see how we ended up with f of x equals 2x. And that's why you're lucky that you don't have to do first principles a great deal in this course. Because it's a lot of work to prove something that's easy to do the
So
short
for
method.
you wouldn't have to substitute anything.
Just erase it.
Yeah.
We actually sometimes negative 2.
Oh, yeah, sorry. I'm sorry. You're asking about that, weren't you? Thanks. Yeah, then we would have to do that, yeah. So I was just thinking,
expense for that now.
I know. If you really don't want to do it, you can cross that off. Because now you know what to do. If you wanted the gradient at x equals minus 2, you would just sub it into it. So if you want, we can
So
cancel
it's
off that.
equal negative 2. I mean, what? Negative 4.
Oh yeah, negative 4, yeah. So if we wanted to know the gradient of this function at x equals minus 2, we would just find the gradient function first. This is the function used to calculate it, and then sub in the x value.
So we would just write f dash x equals negative 4.
Actually, even more specific, maybe let's move on here. Yep. F dash negative 2. That kind of thing, yeah. Equals 2 times negative 2, which equals negative 4. Yeah, because I forgot that afterthought that I said, then calculate the gradient at negative 4. In a way, maybe I should have called this part B. Broken into part A and part B. So part A for this, part B for that. Yeah, because once you've got the gradient function, which is the derivative, then you use it to calculate gradients by subbing in x values. That's how we use them. So, makes sense because this is just a quadratic. It's a regular quadratic. And at x equals negative 2, it would have a negative gradient, wouldn't it? Because it's going down.
And go down.
And then it goes up. So at x equals negative 2, it's going down. So it should have a negative gradient. So you can always critically analyze it. Oh, and the next one. Has everyone got that? Almost? Pretty weird. Okay, now for the function 2x plus squared plus 3. Find the gradient using a secant. Just one more of these. And a tangent at x equals 5. There are some questions in the textbook on whether they want you to use a secant, but really we're kind of more interested in the tangent one because that's really calculus. So let's... Yeah, that f of x plus h minus f of x over h. Yeah, because that comes from... to start with, I just set up a general thing that I knew would make this formula for you. And that's the formula we use for these questions. But for a secant, they're not talking about a limit, it's just talking about between 2 points. So our 2 points are still... Oh yeah, we're still using f of x plus h. We move on from the first principles after this page. So f of x plus h minus f of x over h. And now we've got to apply that thing to this function. A bit more awkward, there's just a bit more to it.
Oh gosh.
Yeah, yeah. So wherever we see x in this function, we've got to replace it with x plus h for the first bit.
Alright.
So 2x plus h squared, which is just a bit more awkward in terms of expanding. And then minus f of x is just minus this thing. So you might want to take into account it's minus 2x squared plus 3. You could have gone straight to saying minus 2x squared minus 3.
Wait, so for that one,
Wait, what?
we
When you put
substituted.
plus 3 over here,
Oh,
could you substitute the 2 in front of the x plus h?
yep.
How
Oh yeah, I forgot the plus 3. Sorry, I forgot the plus 3. Yep, I forgot the little plus 3 in the purple bit.
That was hard people use.
Yes, plus 3, sorry. Forgot that. And then it's minus, and then it's minus this whole thing. So if you want, if you could remember to just go straight to saying minus 2x squared minus 3, you can, or just put it in bracket and minus the whole thing. Because you're going to have to expand and do all this business then anyway, so you can expand this bit then if you want. Yeah, sure. And then don't forget
May you give me a paper towel, please, Sadie?
over h still. So here, because it's a secant, we're not saying that h is approaching 0 or anything. So here we do, that's when we use that. Just at the front of all this, we'd have limit as h approaches 0. then it's a tangent. So now we've got to expand all this stuff, so it's a bit of work. So you're kind of already pretty aware that x plus h times x plus h. Yep, from doing a quadratic foiling and all that kind of stuff. And then I'm going to kind of expand this now, minus 2x squared minus 3 all over, oops, h. I'm making it a bit wide. All that stuff. And then I've got to expand this bit. 2x squared plus 4xh plus 2h squared plus 3. And you'll see each of that's going to cancel out. Minus 2x squared minus 3 all over h. There should be spaces. Okay. What cancels in the numerator? 3. Yeah, 2 as well. Plus 3 minus 3. Anything else? Yeah, squared, yeah. So you'll find heaps of stuff back. Yeah, you could cancel the h's now, but sometimes people make a bit of a boo-boo if they cancel all at once. So if you've got the space, maybe just write what you've got at the moment. 4xh plus 2h squared over h. And then take h out as a common factor. Might be a good idea. H, so we've got 4.
Take out 2 as well. Yeah.
Oh yeah. Yeah, you could. But in a way, you're going to have to put it back anyway. You can, if you want, take out 2, and then you'll just see at the end, you're probably going to factor it back in anyway. The whole purpose of me taking out h is just so I can cancel off the one on the bottom. So yeah, so it's not wrong if you take it out 2h. And just your answer would be the factorised form. Plus 2h, h. Yeah, so that point was just purely to cancel off the h. 4x.
Joe's H-A.
Oh yeah, yeah. 4x plus 2h. That's it. So, because for the secant, they're not saying that h is approaching 0, so we can't cancel it off if it's a secant. It's on the right when it's a tangent.
So what would you say is equal to after that
Yeah, f dash x, yeah. Yeah, or the gradient. Equals, more specifically, just the gradient. Because f dash x is specifically the gradient of a tangent. So you might not want to call that one f dash x. This one you can call f dash x, because the f dash x is meant to be the gradient of a tangent, but this was the gradient of a secant. So because it was a gradient of a secant, the horizontal distance between them is of some note. You know, it could be quite a large value, so we have to kind of leave it as an expression. So the only reason why I did one like this is there was a exercise in the textbook where they want you to find the gradient of the secant. I don't ever see them really in the exams. The good thing is the tangent one is still involving all this red stuff. So if you want, you can say the working. Yeah. So if you want, we can just say C working out, or we'll just write limit to begin with. So let's write the first line. Limit as h approaches 0. F of x plus h. If you want, you can also write equals f dash x, just to remind you. What's that, Kiyoja?
Will we write the cycle?
Maybe, yeah. And then maybe let's just go, and then after that line, maybe let's just say C working out to the left and go straight to the bottom.
Yeah, do that again.
Yeah, we don't want to have to write all that again. So limit as h approaches 0. We will actually fill in the first one where it was subbed in to begin with. Just so you've got this as a reference to see what was going on. 3 minus 2x plus 3 all over h. Again, equals f dash x. And then maybe let's say
Let's too much.
Yeah, I was confused.
Oh, thank you. C, now let's say C working out on the left. So rather than go through all that simplifying again, because it's just the same function, let's go straight to this. Limit as h approaches 0, we still have to write that at this point. And then let's write an expression we've got, 4x plus 2h. Let's remind ourselves what we're finding. We're finding the f dash x, the derivative, the gradient function. And now at that point we can say because h is infinitely approaching the 0, 2h is like almost negligible. It's just so small that it's like almost immeasurable. So we can say our answer is 4x.
So I want
It's
to
what?
write that on the side, like because H is approaching.
No. Yeah.
Just transferable.
But yeah, a lot of people do ask me like, why can we just sub in x is 0 because h is 0 because h is not 0. So I just say why. It's because it's so
So it
small.
basically is there, that's why it's transferable.
Yeah, it's like immeasurable. So it's like an approximation more so, isn't it? Of the gradient. Oh yeah, we need to sub in something there, don't we? So we've got the gradient. This is the derivative. That's where we're having a little thing around it. And then, as Calvin has noted, it wanted the derivative at x equals 5. So x equals 5. F dash x equals 4 times 5. And as Calvin has said, it's 20. Which is another. And then at this point we probably move on and say goodbye to first principles for a while. Oh, yep. I'll also show you a little method on your calculator that you can find the equation of the tangent and the gradient as well. Show you 2 ways. So, what was that? That was it. By the way, does that make sense? Would you agree dy dx or f dash x would be 4x for this function? Yeah. So from now on, we're not going to have to do it like this. We just have to show you this is how that method comes out. Because then people invented the shorthand method. They realized, oh, if you just take the exponent, multiply it by the coefficient, and subtract it, you get the answer. So someone discovered the short method, I can't remember who, and said, hey, let's just use that from now on. Yeah.
Thanks. You can make twice or 3 times.
So I did say don't bother getting your calculator, but it might be helpful to have it. No?
So which equation is writing the x-axis is that or the x?
Oh, to find the gradient, you sub it into the f dash x answer.
No?
No?
Put it in the calculator.
I just graphed the original one. So if you're asked to find, imagine you were instead asked, rather than like using algebra, you were asked to calculate the tangent of the curve using a calculator. This is just a short way that you can do dy dx. So so what you do is graph the original function, go to y equals, graph the original function, let's graph 2x, was it 2x squared plus 3? Oh, okay. Oh, you might not know what to do, that's all.
You press the do that.
Oh yeah. And then you've got to type in,
What's that?
and it doesn't ask you for the x value, you've just got to type in the x value. Yeah, that's probably it. It doesn't prompt you. Yeah, because it doesn't prompt you, which is a bit annoying. Sometimes you're there going, what do I do now? Okay, so you graph the little thing. So it's a nice little parabola. So Piaget's remembered a quick way to find the dy dx, like the gradient at x equals 5. So it doesn't give you the function. There's no way, this calculator won't give you the function, the f dash x function. But if it wanted to know the gradient at one point, you could actually find the number answer, like at x equals 5. So a lot of things we do with graphing is in second calc, isn't it? Like how we find maximums, minimums. So go second calc. Here's a maximum. No, what am I saying? We don't want a maximum. dy dx. Yeah, sorry, number 6. dy dx. And this is where Kiesha was getting confused because she's like, but it doesn't give me anything. what it doesn't ask you, you've got to type in 5. So if they want it at 5, you've got to type in 5. It doesn't ask you for it. It's not till you type in the number that you see x equals 5. So that's a bit annoying. It doesn't prompt you. And see, it gave us 20. Yeah, dy dx is 20. Yeah, that's it. So I might take a snip of that. Yeah, the dy dx is 20. Yeah. So I'll just copy that thing there. So let's maybe write that. So that could be our example. E.g. y equals 2. E.g. y equals 2x cubed plus 3 at x equals 5 could be our example. So y equals, enter the function and graph it. I don't think you even have to graph it. But maybe you want to look at the graph and make sure you get it right. Y equals, and then you go second calc, dy dx, and then you've got to type in 5. So that's the thing that's hard to remember, is you've got to make them type in 5. Yeah. dy dx equals 20.
I did second calc value and I got the
Did you get 20?
No, it's like, you know how she did second calc dy dx? At the beginning I did second calc value and then I put in 5.
And you got 20?
I only get, I got 52.
Oh,
That's the,
yeah, the answer to dy dx is 20. It's the same example as we did manually. So we did it manually up here. I'll just go back, sorry. So that's just how you find the gradient. So that's a gradient of the tangent. If you just want the whole equation, so that's a gradient of the tangent, so you know what the tangent at that point, like the tangent at that point is going to be 20. But remember the tangent, so the whole tangent equation, a straight line is in the form of y equals mx plus c. We know the gradient's already 20, but imagine if they just wanted to know the gradient, that's fine. But if they wanted to know the whole tangent, like the straight line, what was the y-intercept and its gradient at x equals 5, then there's another thing you can do. So you have to have graphed it. So this is something you might not have learnt to do before. So you have to have graphed it. And can you see draw? Second, this is one that you'll hardly ever use. Second, draw. See, draw's about here.
Oh, I see it, yeah.
So, and so you've got to press second first and then draw. And then which one do you think I select here to do a tangent?
Maybe.
Yeah, number 5, tangent. And again, it doesn't prompt you. So what should I type in? 5, yeah. It's not till you type in your number that suddenly x equals pops up. So because at 5, and then you press enter, and look, it's going to draw the tangent. So you drew my tangent, and there's a little equation. Amazing. So the tangent, oh gosh, where's it gone? So here we go. Our tangent's right up here. I'll adjust my window a bit. I'm going to adjust my window a bit. That? Yeah, sure. I'll go up to 20 maybe. Just so that you can see it. I just want you to see the little tangent. Oh, come on. It's probably even higher, isn't it? Yeah, it's higher. I should have made it higher. So, I'm just making... You don't need to do this. You don't need to view the tangent at all, like where the point is. I just want to show it to you. Second, and then draw. It's programmed. The actual button is PREM. So second, draw. I just know it's around there somewhere, and I always have trouble finding it. So I have to scan around a bit. So I just remember, because you're drawing a tangent. Where's the tangent gone? Okay. I made it up to 100, but I want to see the tangent. I probably have to do it again. That's probably why it's gone. 5. So I just did second draw, typed in 5. There it is. There's my little tangent. So see,
Wait, what did you do?
yeah.
What did you do, Miss Melanie?
So I just did it again, but because the point where it touches at x equals 5 was so high up, I made my window y max up to 100. So I made you don't have to view it. It's just I wanted to show you. Might be a bit more interesting. So do you see, Talise, like, I just zoomed out a bit, and so now I can actually see where it does it. You don't need to see it, though. All you need is the equation.
Dog, my calculator.
Yeah. So the good thing is, with intersects, you have to adjust the window so you can view it. But with tangents, you don't have to, and dy dx's. So there's our gorgeous little tangent. So,
Did you get 20x plus 47?
did you? Yeah, it makes sense too. And this is a line. It's got a gradient of 20, so it's really steep. Did it change colour?
I could change the width of the line.
So for this one, you might want to note that you have to have graphed it first too. Second draw, select 5, tangent. Are you talking to me, sorry?
I don't know what happened. I changed my window and then I did second and now it's actually.
Can you not?
Oh, you have to type in 5. Did you type in the 5? Remember, it doesn't prompt you. You have to force it in. Like, as in, like,
Don't do it
it
again.
doesn't ask you to type in 5.
So you come to me.
Is it minus 47? That's our answer to the tangent.
You got it from Cookers.
So you see, it is a tangent. It cuts at one point only, and it's a line that goes that way.
Yeah, then it intersects and goes over the other side.
Yeah. So that's a pretty neat thing. If it's a calculator problem, you can just find the equation of a tangent by doing that. So what's the y-intercept of this tangent?
Negative 47.
Yeah, good. What's the gradient of that tangent?
Same. X squared is what it actually so in that equation does that mean 20 what you beat the two this one.
So what is the value of the gradient of this function at x equals 5?
2.
Close?
No, 5.
You said it before, 20.
No.
So the gradient of this function at x equals 5 is 20.
It's not y equals 2x cubed.
Oh yeah, I keep forgetting. Oh, did I just write cube? Where did that come from? Okay. Sorry, that's 2x squared. I think so. Okay, that's good. That's a sweat. So, Paige, we just showed people how to draw a tangent by going second draw tangent. And you type in 5. Again, it doesn't prompt you, so you've got to type in 5. And then see, Paige, it draws a little tangent for you. Paige, look, it's exciting. It drew the little tangent, and then it gave up me the little equation below. So that way is a quick way to just get the gradient if you need it. But if you need the whole equation of the tangent, like because tangent's a straight line, like y equals mx plus c, this gives you the y-intercept as well. And it's second draw, which is a weird spot. Draws somewhere around here. Bit weird. So now we move on to the little shorthand method. So we're about to, on the next page, we've still got a few minutes, let's do some more. Let's do some practice of shorthand calculus. No, not first principles.
You did it.
So this is just... What? Okay, so this is a little short method that you know already. So instead I'm just going to, I've given you some harder examples with lots of fractions and weird exponents and stuff. This is the short method that you learned in GCSE. Basically you multiply these something. Exponent.
You don't have no E.
You don't have an E?
I would have an E because you don't punch it out.
Huh?
And you also put X in it.
I know. Yeah, you'll notice I fixed it on mine, but I didn't fix it on yours. So
Okay.
I had exponent, not exponent.
One.
Yeah, good. One less. Good. You multiply the above.
Like, when you do 3x squared, it becomes 6x.
1.
Yeah.
Okay.
Yeah. So if you do, so from doing first principles, this pattern emerges that this is a shorthand way to do it. Rather than have to do that whole first principles method, this is just a short way to get straight to the answer. So as we said, the notation to use, if the original function is y, we call the derivative dy dx. Yeah. So that's a notation. If the original function is in the form of f of x, the derivative is, we say f dash x. Just so you understand the notation. So if your original function was y, call the derivative dy dx. If the original function is f of x, call the derivative f dash x. Was that to do with the fight between Leibniz and Newton, the different notations? I think the f dash was kind of Newton. I can't remember. I probably got it the wrong way around.
Is it?
Okay, yeah, and Leibniz was kind of all this other stuff, so maybe he was dy dx, I don't know. So that's probably why there's a conflict, why there's two. In GCSE, they only gave you dy dx, and now we're in IB, we also I personally find it faster.
I gotta get
But then you have to decide
that
if
you know?
why it's right. Okay, so find the derivatives of the following. So we're just using the short method now, none of this first principle stuff. But I'm just trying to give you a slightly trickier one. So I gave you y, so call the derivative dy dx. So call it f dash x. So what would be the new coefficient of this one? 2.5, yep, or 5 over 2. Does it time to do that too? 2.5. That's correct, 2.5 is fine, or 5 over 2. X to the power of 4, yep, you're right. Minus 9x squared plus 2x minus 0.2. And then constants don't appear. So that's done. If I wanted to know the gradient at x equals 1, what would I then do?
How come, what about the negative 5 over 9?
Yeah,
So
there's
we
no
get
x
rid of
in it,
that?
so it's a goner. If that helps you realise that it's gone.
What would be
One.
how you
Going
put
to track
the-
1.
So if I wanted to know the gradient now at x equals 1, what would I have done?
Wait, why does it equal? Why do you cut it out? I'm sorry.
Oh, there's no x, there's no x
They
in
don't
there.
matter. We
Yeah.
talked to this. Sorry, I forget. I need some reiteration. It's a new topic for me.
And if you did it with first principles, like you know how when we do first principles, certain things cancel out a lot? Like I'll show you.
So
Like,
the
the
8, you don't have
like see these ones, the 3's cancel out.
Okay.
So the constants always cancel out with first principles.
Oh, that's what I need to know.
Yeah. Yeah, so now you sort of see a bit of a reasoning behind it. Okay, so that's done. So if I needed to know the gradient at x equals 1, I would just sub in x equals 1 into f dash x. Right. So the derivative of the f of x is f dash x. What would be my coefficient? Yeah, 0.3 or as a fraction? I just want to use a fraction.
over 10.
3 over 10, yep. Because 3 fifths times 1/2 is 3/10. Now this is awkward. What's the new exponent?
So the negative 0.5.
Yep. Negative 1/2 or negative
Because negative
0.5.
half minus 6.
Minus 6, yeah. So that's totally okay. If you then had to use the gradient function though to do some solving and stuff, you might be better off popping the negative exponent underneath. To make them positive. So to plot the x, notice the negative 1/2 only belongs to the x. So it's like saying 3 over 10x to the positive 1/2 minus 6. Just showing you that both are okay. This version might be easier. Or you could write 10 square root of x. Same thing. Because remember square root is like 10x to the 1/2. So both are fine. If they just want the derivative, that's fine. But if you need to use it to solve or do anything, sometimes that's better. Yes?
Why wouldn't we just simplify the 3 over 10 to just a third?
Oh, because it's not a thing.
It's not a thing.
It's 0.3. That's a good point though. If you can simplify the fractions, definitely simplify them. Yeah, 3/9 is a third, yeah.
Like that's the
But yeah, if you can simplify them, you definitely do. Yeah, we'll finish up there because this will be nice to do as a warm up.
What?